I'm just kidding. All right, so guys, again, at the risk of this feeling rushed, we're going to move through this not at a hurried pace, but at an appropriate pace. And guys, as we move through this, what you're going to find is this is all about skills. But before we build these new skills, we need to look at the last homework assignment. So guys, grab this thing and let's talk through where you need to be. So guys, and if you need more, tell me. But guys, my suspicion is the top part of this, you were okay because you just copied it out of your notes, right? Then guys, this, as a result of what we did last time in class, you were now able to answer question number 2. And guys, question number 2 was all about the orbital filling order from the 1s all the way out to the 7p. And guys, you probably noticed that when you got into this region, things got weird. We start in the S, we jump to the D, we fall into the F, we come back to the D, we go out to the P, and then we rinse and repeat. Guys, here's the deal. You don't need to worry about this. We will never be doing chemistry with the elements that lie below the 5p. As a result, you do not need to worry about the complexities of how the 6 and 7, S, P, D, and F all interact with each other. If you'd like to understand and you don't understand it now, I'd love to sit down and talk with you about it, but we're not going to hassle with it right now. So guys, if you were good through the 5p, you're totally fine. Then this. So guys, down here, you didn't have to draw the pictures, but you need to know that the S is a sphere. You need to know that the P's are dumbbell shaped. You need to know there's 1 and there's 3, and then they orient 90 degrees to each other because of repulsion. You okay there? Okay. Then guys, this. Let me go here. Let me go here. Let me go here. And now guys, we need to slow down for a second. These you've got to be able to do. This was the big idea, not just from last time, but frankly from the unit. So guys, these are things that you need to be able to do. As a quick refresher, guys, if we start down here on one that's a little bit bigger, like maybe chlorine, guys, remember that chlorine is in a P sublevel, but specifically that is the 3p sublevel. So we go out, but we've got to place the first 2 electrons in the 1s, then the 2s, then the 2p, then the 3s, then the 3p. And then guys, we write those out. We go 1s, 2s, 2p, 3s, 3p, and then we place the orbitals. And guys, we understand that the S has 1, the S has 1, the S has 2, the P's have 3, and so on. And then guys, remember the way we place electrons. We go 1 and then 2, 3 and then 4, and then remember these have to spread out. 5, 6, 7, 8, 9, 10. And then when we finally get down to electron number 17, that is 1 box short of the end, and that is represented by that 1 empty space right there. So guys, a little bit of a refresher. What questions do you have on any of these? Not just this page. You okay? So guys, understand if you don't have questions right now, and because you didn't come in and ask questions outside of class time, I'm going to operate under the assumption that you have a mastery of these so that we can then go forward. So guys, please, I know it's early, I know it's quiet. Is there anything I can do to clarify for you? Nora? Yeah? Mm-hmm. Yeah. Yeah. Uh-huh.
So, my question is, why were those like different shapes? Because, or like sizes? Just because are they the same, or is it just representation?
No. They're very much sizes. So let's talk about why. So I was watching your hands and you said small sphere, then bigger sphere, and then figure eights that were about the same size as the sphere. So functionally, what's correct? Right. So the little sphere was the 1s, then the bigger sphere was the 2s, and then those 3 dumbbell shapes were the p's. But notice they're the same size as the s. So the orbitals, I'll just go right here. The orbitals within a sublevel are pretty close to the same size. The P are a little bit bigger, but they're functionally the same size. And then the third energy level, these would all be functionally the same size. So everything within an energy level with that same leading number, they're the same size. And they do get bigger because we need more space for more electrons. Is that okay? Awesome. Guys, what else? Are we good? Okay, so guys, we are not going to grade homework, but don't put it away. We're going to record this at the end of class today, but guys, do not put your homework assignments away because if this goes well, and again, I've never done it this way before, guys, if this goes well, you may have time for homework. Let's see how we do. So guys, what I've done is I printed for you your class notes. So all you need is this, and guys, this is super duper fill in the blanks. So let's take a look at this and let's see where we get. All right, so guys, let me clean up my space like so, and like so, and like so, and like so, and then grab a hold of this, and then this. So guys, allow your eye to scan through this notes page. And here's what you're going to notice. There are 3 sections that are headings that are underlined. And guys, find those 3 sections. Section 1, representing ions. Section 2, noble gas abbreviations. And Section 3, Lewis dot structures. Do you see it all? But then guys, notice the pattern. After each one of those headings, there's a little bit of notes, right? There are supporting ideas. But then, guys, following that, what repeats itself 3 times? Orbital filling diagrams. And I gave them to you. So guys, join me at the screen and let's talk about how this flows. So guys, what we're going to do is we're going to take orbital filling diagrams and we are going to use them for the foundation of representing ions, doing noble gas abbreviations, and then doing Lewis dot structures. But guys, functionally what we're going to do is this. We are going to use these 4 orbital filling diagrams as the foundation for what we're doing. So guys, do this with me. Find sodium on your periodic table. We're going to talk about sodium all day. Find it on your periodic table. Guys, sodium is in the 3s sublevel. Which box is it in the 3s, the first or the second? The first. Guys, do you understand that that corresponds with this electron? There's 1 electron in the 3s because sodium's the first box in the 3s. Now guys, find chlorine. If it's helpful, put your finger on it because we're going to be talking about it all day. Guys, when you find chlorine, how far is it from the end of the 3p? 1 box. Do you understand that that represents this empty space? Okay, then guys, find copper. You actually did it in homework. Guys, copper is element 29. Do you see the connection between the 1 box away from the end of the 3D and this empty space? Okay, then guys, do arsenic. It's down in the 4p. 4p? Yeah. Guys, do you see the connection between these 3 electrons and arsenic being 1, 2, 3 into that p sublevel? You seeing the connections? Okay, so guys, with this as a foundation, what we're going to do is this. We're going to check these off one at a time. We're going to do ions, we're going to do noble gas abbreviations, and we're going to do Lewis dot structures, all based on these ideas. Do you have the foundation with me? Okay, so guys, why are we doing this? And guys, the answer is this. These diagrams, these orbital filling diagrams, do a great job of telling us the complete electron structures of these atoms. But guys, frankly, they're a pain in the butt. All these arrows, all of these boxes, this is ridiculous. And so guys, what we've got to do is we've got to make these simpler, because we're going to be representing these for the rest of the year, but we need easier ways to do them. And that's what we're going to talk about today. So guys, let's do this first, and let's talk about ions. Guys, there are fill in the blanks in your notes, but I'm going to click through these quickly because guys, you already know this stuff. Back in Unit 2, when we talked about the number of protons, neutrons, and electrons in an atom, we talked about ions. So this is a review. Guys, ions are atoms with a charge. I'm going to follow along in the notes because I've never done this before, and I want to make sure. And by the way, guys, please, if you see mistakes or places where you're like, my notes don't line up with the slides, please let me know. I made this up late last night, and it could get funky. So we're okay so far, right? Ions. And then, guys, you might remember this. There are positive ions and there are negative ions. The positive ions are called cations. Not cations, but cations. Guys, cations are positively charged, and we create them by removing electrons. Remember, positive charge take away electrons. Then, guys, this. Negative ions are called anions, and anions are negatively charged, and we form these by adding electrons. Is that all coming back to you? Guys, let me do an even better job of refreshing your memory, and please don't write this down. Guys, this is the context where we learn this stuff. Again, find chlorine on your periodic table. I really don't remember. Is it element 17? Is that right? So guys, chlorine is element 17, but it has a mass of 35, so that means 17 protons, and that means 18 neutrons, and then guys, 17 electrons in orbit. This is starting to come back to you. And then guys, we did this. If we want to make chlorine negative, what do we do? Again, if we want to make chlorine negative, what do we do? Add electrons. What if we want to make chlorine positive? What do we do? Take away electrons. But guys, here then becomes the question. If we want to make chlorine positive by taking away electrons, the question is, which ones? So guys, before we just said, hey, yo, chlorine, take away electrons. But now we know that its electron structure is this. So which electrons do we take away? And it's not quite. It's actually a little more complicated than that. Guys, what we do is we take them out opposite the order they went in. So remember when we place these, we go 1, 2, 3, 4, 5. So guys, when we take them back out, we do it in the opposite order. We go 5, 4, 3, 2, 1. But then the question becomes this, guys, when does that stop? When can we no longer add or remove electrons? And the answer to that is actually the next thing in your notes. So guys, the concept is this. When we add or remove electrons, we always take them or put them in to the highest S and or p orbitals. And guys, these are what are called the valence orbitals, and that means on the outside. So you guys ready to make a horrible mess? Guys, go down. Are you all caught up? The blanks are pretty straight. Are we good on blanks so far? Okay, so guys, go here with me. And let's start fiddling with these atoms and let's start turning them into ions. Guys, do this with me. make a mess. So guys, let's take sodium and let's turn sodium into, let's do the other. Guys, let's turn sodium into -1. And I want to grab a bigger pen so this stands out better. But guys, let's turn sodium into -1. Do we add or remove an electron? Add an electron. Where does it go? Right there. And that would be sodium -1. Guys, do this with me. Now, guys, what about this? What if we want to take sodium and what if we want to make sodium -2? How many electrons do we add? 2. There's one of the electrons. Where does the other electron go? And the answer is nowhere. There's nowhere for that electron to go. And therefore, guys, sodium can't go -2. There's nowhere to put the electron. Does that make sense? You guys okay? Okay, then guys, do this. If you can erase, that would be great. If not, you'll be fine. But now, guys, let's do this. Let's make sodium +1. What do we do? Add or remove an electron. Remove an electron. And guys, we're going to take away that electron right there. But now, guys, let's do this. Let's make sodium +2. Which electron do we now take away? Guys, the answer is you can't. The valence electrons are the highest S and or P. And guys, the highest is 3. And because the highest is 3, it means that these are off limits and you can't touch them ever in sodium. And so, guys, resetting the clock, all that sodium can do is +1 and -1. That's it. If we try to go -2, there's nowhere to put the electrons. If we try to go +2, we don't have a second electron to take away. Does that make sense? Questions? Okay, then guys, let's go down to chlorine. What if we want to go chlorine -1? What do we do? Add an electron right here. Guys, what if we want to go chlorine -2? You can't. Chlorine can't go -2. But now, guys, this is kind of getting, I'm going to have to do this right-handed to stay out of the way. Now, guys, let's do this. What if, okay, guys, what if we want to go chlorine +1? Do you see that it's not this electron that we take away, but it's the last one that we placed, and that would be this one? Is that okay? Then, guys, I'm going to just kneel to do this. So what if we want to go chlorine +2? Does it make sense that we're going to take away that one? Then chlorine +3, this one. Then chlorine +4, this one. Then chlorine +5, this one. What if we want to go chlorine +6? We can do that because, guys, this is the 3P and this is the 3S. So this is off limits. But, guys, we can go +6. We can take away that. And we can go +7 and we can take away that. But, guys, we can't go +8 because we can't dip below the 3rd level. Does that make sense? You okay? So, guys, you're going to see questions on the test that ask you things like this. What is the lowest negative charge that chlorine can take on? And the answer is -1 because it can't take a second electron. Guys, what is the largest positive charge that chlorine can take on? And the answer is +7. Relating these to the orbital filling diagrams, does that connect? Okay, now, guys, here comes a curveball. Ready? Copper -1. Where does the electron go? You can't. Guys, copper cannot go -1. You're going, wait a minute, there's a space right there. But guys, understand the highest S&P is the 4. And as soon as we start the 4, there isn't a 3. And guys, this space is not available to take electrons, so copper cannot be negative. So now, guys, let's talk about positive. So what if we want to go copper plus 1? Can we do that? Where does it come from? 4s. Guys, this dude goes away. What if we want to go copper plus 2? Yeah, we can do that. And this dude goes away. But guys, we can't go copper plus 3 because we can't dip into the third energy level. Are you seeing the patterns? Guys, questions about any of that? You okay? So now, guys, let's look at arsenic. Thumbs up or thumbs down? Can arsenic go -1? Yes or no? Yeah? Where's the electron go? Here. -2? Yeah. What about -3? Yeah. What about -4? Do you see why? Know where to put it? Okay. But then, guys, thumbs up or thumbs down? Can arsenic go +1? Yeah. This electron right here. +2? Sure. Take this away. +3? Also yes. Guys, this one I really want to see your thumbs. Can arsenic go +4? Yes or from where? Yeah, down here, guys. It skips the D and it steals it from the S. And then it can also go +5, but it can't go +6. So guys, we are crushing it. Take a breath. Do you understand the rules and the patterns for doing ions now that we understand what the electrons are really doing? You guys okay? Okay. So gang, now that we've established that, we are now going to chip away. Oh, this isn't going to let me switch. No, hold on. So guys, we are now going to chip away at the other ways that we can represent these structures. Guys, so now you see the next heading, noble gas abbreviations. Guys, right now my mind is absolutely whirling because we've never taught this efficiently. I'm really curious to see how long this is going to take. Anyway, so noble gas abbreviations. Guys, noble gas abbreviations communicate the same information as the orbital filling diagrams. And now I need to reference my notes. So guys, they provide all the same information as the orbital filling diagrams with a couple, it makes it smaller. And guys, it does that in two ways. You do not draw the electrons as arrows. Instead, and you have to fill in the space, right? Instead, you use a superscript to count the total electrons in each sublevel. Then, guys, the other simplification is this. Finally, you don't have to start at hydrogen every time. Instead, you can start at the nearest noble gas. What did I give you for fill-ins there? Begin at, is it nearest noble? No, at nearest preceding noble gas. So guys, in order for this to make sense, you need to know what the noble gases are. Some of you know, some of you don't. Let's get up to speed. Guys, these are what are called the noble gases. Let's talk about why we call them the noble gases. And you know enough to understand this. Guys, the noble gases are at the end of the P sublevel. That means that their P sublevels are completely full. But if their P sublevels are full, all of their S's and D's and F's also have to be full in order to fill the P. So guys, what that means is the noble gases have no empty spaces in them. That's why we call them noble. They don't react. They're full. And because they're full, they don't need electrons. And as a result, they don't react. So we call them noble because they're standoffish. So guys, check this out. Going back to this. Is this on the back of your notes? Yeah? Okay, flip over. So guys, here's the deal, and let's just say it. Guys, these orbital filling diagrams, while they're interesting, they're a pain in the butt because they're so bloody, stinking redundant. Guys, if you look, and I know some of you even got frustrated with this, it's always the 1s, it's always the 2s, it's always the 2p, and they only get different at the end. So you end up writing the same stuff over and over and over, and the only time it changes is at the end. So guys, what noble gas abbreviations let us do is get rid of all the redundant stuff and only write down the stuff where it changes. So guys, join me, and we are going to turn these into noble gas abbreviations. Guys, find sodium on your periodic table. Now go backwards. What is the closest preceding, that means before, noble gas? Neon. Now guys, watch. Where is neon? Neon is at the end of the 2p. So guys, this is what we're going to do. We're going to go this, and guys, do this with me. This right here is neon. So we are going to replace this with neon in brackets. Now guys, this, how many electrons are in the 3s? 1. Make it a superscript. And guys, when we do that, we end up with this. Neon 3s1. That is the noble gas abbreviation for neon. Does that make sense? So guys, let's do chlorine. Element number 17. So guys, what is the closest preceding noble gas? Not argon. Argon comes after it. What precedes it? Neon. So guys, again, this is neon. So we're going to, in brackets, go neon. And then in addition to that, we've got the 3s with 2, and then the 3p with 1, 2, 3, 4, 5. Is that jiving for you? So guys, do this. You guys picked up on this last time in class. You guys realize these are all on your periodic table, right? Find them. They're right between the name and the abbreviation. So guys, sodium is neon 3s1. See it? Now guys, find chlorine. Do you see how chlorine, oh actually they did chlorine the same. That's good. You good? Now guys, do this. Look away from your periodic tables and join me at the screen, and let's do copper. So copper is here. Do we go to krypton or argon? Argon, and that's at the end of the 3p. So guys, all of this is argon. So we're going to go argon in brackets, and then in addition to that, we've got the 4s with 2, and then the 3d with 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3d9. Now guys, look at your periodic tables and find it on there and find the differences. Just a second. So guys, look at it on your periodic table and find the differences. There's 2. What are you seeing? Yeah, they switched the order. Guys, let me explain to you why they do this, and then I'll tell you what we're going to do about it. So guys, on our periodic tables, they switch the order. The reason that they switch the order is they will always put the valence electrons last. Guys, the 4s are valence, the ones on the outside, the ones that we can give and take. The 3d is not valence, so they always put the valence electrons last. We're not going to do that. Guys, we're going to go the order that they fill, which is 4s and then 3d. But did you notice the other difference? Yeah. Guys, this says, wait. Does yours have 4s2, 3d9? That's interesting. My periodic table has a typo in it. So guys, let's just grab the more recent version of the periodic table. So you really see that, Nate? Is that right? So guys, if you look at copper, does yours... Yeah. Okay, do you see it? Guys, if you look at copper, yours says 3D10 4S1. Yeah? That's exactly what's going on. Guys, but Nate's right. Let me show you and then talk with you about it. Guys, what actually happens is this. One of the electrons jumps out of the S and into the D. And guys, the reason it does that is stability. But I don't expect you to know that. So guys, when you do copper, what we would put for copper is simply argon 4s2 3d9. Is that okay? All right, so now guys, let's do this. Let's skip arsenic and let's go to the next page, the next part. And guys, the next part is this. You need to know how to draw noble gas abbreviations. But guys, if you have to draw the orbital filling diagrams in order to do the noble gas abbreviations, that's more work and not less work. So guys, looking down, I believe, oh, it's not going to let me switch. Guys, looking down, I think in your notes, guys, what we've got to be able to do is this. We've got to be able to do these without drawing the orbital filling diagrams first. And we're going to be able to do these without just looking them up off the periodic table. Guys, be careful. If you just copy the answers off the periodic table, many times they're wrong because they're out of order and they're representing electrons jumping around that we don't worry about. So guys, find magnesium on your periodic table, element number 12. Let me show you how to do these right from the start. So guys, magnesium is right here. What noble gas do we go back to? Neon. So guys, what you're going to do this with me. You're going to draw a bracket, and then you're going to draw neon. Now guys, in addition to neon, we are in the 3s sublevel with 1, 2 electrons. So guys, this is 3s2, and that's magnesium. Now, does that match up with what's on the table? Hey, it worked. Now, guys, let's do this. Gallium is element number 31. What noble gas do we go back to? Argon. So, guys, we're going to go argon, and, guys, capital, then lowercase in brackets. And then, guys, in addition to argon, check it out. We're going to go 4s with 2. Go ahead and write it down. The 4s with 2. So we've got 4s2. Then, guys, we've got the 3d with 2, 4, 6, 8, 10. So the 3d with 10. And then we've got the 4p. But, guys, how many electrons are in the 4p? Just 1. How we doing? Good? So, guys, now we got to do ions. The last 2 are ions. So let's grab iodine and let's do this. So, guys, iodine is all the way down here in the 5p sublevel. So we go back to krypton. And in addition to krypton, we go 5s with 2. We go 4d with 10. And then, guys, we go out here to the 5p. And we go 1, 2, 3, 4, 5. So, guys, iodine should be 5p with 5. But if we make it -1, it's 5p6. And that's it. So that would be iodine -1. Now, guys, this. Here's strontium. We go back to krypton. And in addition to krypton, for strontium, we've got 1, 2 electrons. But guys, what do we do to give it a +2 charge? Take them away. So guys, this is what you do. You go 5s0. Don't erase the 5s. Put 5s0 so that you know there should be electrons there, but now they're gone. Guys, we are seriously killing it. Yeah. Mm-hmm. It's a great question. Let me, Adam, if I may, follow up on your first insightful thought, and then we'll talk about your question. So check this out. Take a look at iodine with a -1 charge. So iodine is here, right? But when it takes on a -1 charge, it takes on the electron structure of xenon, a noble gas. When strontium loses electrons, it takes on the electron structure of a noble gas. What you're going to find out in the next unit is that when atoms gain and lose electrons, we call it bonding, what they're actually doing is trying to take on the electron structure of a noble gas. And so we're going to get to that later. But then your question was, if we take these 2 electrons away from strontium and it takes on the structure of a noble gas, will it take them back? And the answer is yes. And the reason is because strontium still has 38 protons in the nucleus. So strontium has a positive charge that can still support 38 electrons. So it will happily take them back. Yeah. Yep, absolutely. It is, all of this is stability stuff, which frankly kind of makes me sad because we used to spend an entire day and talk about what's called the stability pyramid. Nate brought it up first. This is all about stability. But they wrote it out of the Gen Chem curriculum, and so we sort of, bowed to the powers that be. All of this is about stability. Yeah. Guys, other thoughts or questions about noble gas abbreviations? We are killing it. Guys, you're looking at these and you're going, I now understand that these are simplifications of the orbital filling diagrams. Well, guys, we're going to make these even more simple. How are the notes doing so far? Are they keeping up? Is it right? Okay, so guys, now Lewis dot structures, and let me turn to the notes. I'm okay on the back. So guys, here's how Lewis dot structures make this even more simple. Lewis dot structures only represent the valence electrons, but they represent them as dots surrounding the abbreviation of the element. So guys, let me do a better job of explaining this, and you've got this in front of you. You, of course, see that this represents the S and this represents the P, right? Are yours labeled? They're already there? Okay, so no surprise. Now, guys, why are the S and P electrons important? And the answer is because they're valence. They're the high ones. They're the only ones we can mess with. But guys, you know the pattern, right? Write down what you need. When we start filling the valence orbitals, number 1 goes there. You can write 1 underneath it if you need. But guys, where does number 2 go? Paired up. And then, guys, what about electrons 3, 4, and 5? Each box. But then, guys, 6, 7, and 8 have to pair up. So, guys, this pattern is the pattern that we use to do Lewis dot structures. And, guys, it goes like this. We are going to do some fictitious element X. And guys, what we're going to do is we are going to envision that this box represents the S sublevel. And then we're going to envision that these 3 boxes represent the P's. But guys, watch the screen. We don't actually draw the boxes. We envision as if they're there, but we don't actually draw them. And then guys, we just repeat this pattern. Electron number 1 is that dot. Guys, do this with me. If this is electron number 1, where does electron 2 go? With it. Then guys, 3, 4, and 5 go unpaired. 3, 4, and 5 go unpaired. That's a great question. And Adam, the answer is it doesn't matter. It does, so long as they're unpaired, it doesn't matter. What you're going to find out is it actually doesn't even matter if we put the S on top. We could put the S on any one of these faces. We just need to know the first 2 electrons are paired, and after that, the next 3 are unpaired. Then guys, 6, 7, and 8 pair up. So guys, let's take this idea and let's apply it to our pictures. You ready? Oh, I need to turn my board back on. So guys, this takes us back around to what we talked about at the very beginning of the day about valence electrons. There we go. So, oops. Oh shoot. That was bad. All right, so this takes us back to what we've said about valence electrons. And guys, it goes like this. These electrons are untouchable. They are not valence. Therefore, guys, we only have 1 valence electron in sodium. So we just go Na and we draw a dot and we're done. That's it. That's the Lewis dot structure for sodium. Now, guys, we do chlorine. These electrons are untouchable. They are not valence. So then, guys, we go Cl, and then we start placing our electrons. 1 and 2 pair up. But again, guys, it doesn't matter where they go. Top, bottom, left, or right. Let's just stick them there. Doesn't matter. They just have to be paired. Then, guys, 3, 4, and 5 pair up or go unpaired. 3, 4, and 5. And then 6 and 7 go paired up. Did that pattern make sense? Now, guys, for those of you that are looking over the horizon, you don't need to draw this. This one's for free. You see this electron? You see this space? Table salt. Guys, that's how this works. These spaces fit together like puzzle pieces, and that's how table salt forms. We'll talk after Thanksgiving, but guys, that's how table salt forms. So now, guys, let's go down to copper. So, guys, copper's valence electrons come after this. But then, guys, what about the 3D? Are they valence? No. So, guys, copper has only got 2 valence electrons. So we go Cu, and then we need 2 dots. It doesn't matter where they go. They just have to be paired up. And then, guys, finally, arsenic. This is our preceding noble gas. We've got valence in the S. We've got valence in the P. Guys, I'll write this up above so you can see it. So we've got arsenic. And then, guys, we've got these 2 electrons, 1 and 2. And then 3, 4, 5, unpaired, 3, 4, 5, like so. How we doing, gang? Okay. So guys, then this. We need to be able to draw these Lewis dot structures without drawing the orbital filling diagrams first. We need to find the pattern. So guys, do this with me. How many dots does sodium have? I know mine's a mess, but you can see it. How many dots does sodium have? 1. Find it on the periodic table. Guys, how many dots does chlorine have? Count them off the board. How many dots does chlorine have? 7. Find it on the periodic table. We're going to skip copper. How many dots does arsenic have? 5. Find it on the periodic table. Do you see the pattern? What's the pattern, Nate? Yeah, good. Why do we skip the D? They're not valence. Guys, check this out. Sodium has 1 dot. All of them have 1 dot in that group. Guys, chlorine has 7 dots. But guys, watch to make sure you get this. Chlorine's got 7 dots. 1, 2, 3, 4, 5, 6, 7. Arsenic's got 5 dots. 1, 2, 3, 4, 5. But now, guys, let's talk about copper. How many dots does copper have? 2. But guys, what about the 9 dots that are in the D? They're not valence. So guys, all of these have 2 dots because their D electrons aren't valence, but you have to fill the S before you get to the D. So guys, it goes like this. 1 dot, 2 dots, 2 dots, 3, 4, 5, 6, 7, 8 dots. So guys, with that said, check this out. Guys, let's do these. So guys, find magnesium on the periodic table. It's right here. How many dots? How many dots? But guys, this is the only way you can screw this up. This is wrong. Why? They're in the S. They got to pair up. So guys, that is not correct. It doesn't matter where you put your dots. You just got to put them together. So guys, this works just fine. So now, gang, let's do gallium. Gallium is right here. It will have 1, 2, 3 dots. Skip the D. So guys, gallium's got 3 dots. The first 2 are paired, and then the third one just needs to be unpaired. It doesn't matter where it goes. Then guys, we've got iodine. Iodine's got 1, 2, 3, 4, 5, 6, 7 dots. So guys, iodine has got 1, 2, then 3, 4, 5, 6, 7. But now we need to give it a -1 charge. What do? Add an electron and it goes right there. But guys, check this out. If you do this, it's wrong. Do not put charges in your Lewis dot structures. So then you're going, wait, how does anybody know that this is a -1 charge if it doesn't say it? Because you're going to get so familiar with these that you're going to know that iodine should have 7, and if it's got 8, it's got a -1 charge. So now let's do selenium. Selenium is right here. It's got 1, 2, 3, 4, 5, 6 dots. So selenium goes 1, 2, 3, 4, 5, 6 dots. But then, guys, if we want to go selenium +1, what do? Take 1 away. Which one? One of the pairs. This was the last one I placed, so it would be the last one to come out. But guys, you could also take this one. You just have to take a paired electron first, and it would be that. Now, guys, we're back to calcium. What are we going to do? Calcium's got 1, 2 dots. So we go calcium, 1, 2 dots. But then in order to give it a +2 charge, we take those dots away. So that would be calcium plus 2. Don't put the charge on it. Guys, holy smokes. Let's grab our homework packet. Let's talk for a moment. And then I have another question for you. So guys, turn to assignment number 3. Sorry, 4. So if you read the instructions, it says write the noble gas and Lewis dot structures for these atoms, and it is two-sided. This would be my suggestion to you. Guys, on the front of this, do the noble gas first and the Lewis dot second. Then on the back, do the Lewis dot first and the noble gas second. That way you don't get reliant on the noble gas to do the Lewis dot. Know what I'm saying? Okay. So guys, that is your homework. Here's the problem. I'm going to be gone on Friday. And that means if you need more support on any of this, our last available is tomorrow. But guys, the other additional problem is that I have a doctor's appointment at 2 o'clock in Salt Lake tomorrow. And so I'm not going to be here after school. So I'm going to make myself available during lunch, and I'll be here in the morning. And guys, I'll also be available to you today after school. I'll stick around for a little while. So if you want to come in during 4th, I'd love to help. So again, today after school, tomorrow morning, tomorrow lunch, that would work great. So come by if you need. So guys, I'm going to stop recording, and we're going to get going on homework.